I am finally getting around to putting together a video about multiple linear regression. So I'm going to do a lot of talking and pointing, clicking, and stuff like that. Unfortunately, I don't have a really strong writing tool. Maybe I'll open up a Word document and do some. Maybe I can do. I can type out some of this stuff to assist. So I'm gonna start kind of at the beginning of multiple linear regression. Remember, the whole idea with multiple linear regression is that we want to take multiple explainers and try to predict a response. So we have something that we're trying to predict, maybe sales, maybe changes in stock price, maybe the amount that a company is going to earn in investments, or anything that we're interested in predicting. That's our why. And then we use a whole bunch of different things to try to predict it. So we use every explanatory variable that we think might be related to whatever our y is, and we can throw that into a model and use that to predict. So we don't just use one thing, we use a whole bunch of things. So that's called multiple linear regression. And so I'll just use the lipid data set. Remember, you can get this in the help menu. So if you want to follow along, if you go to the help menu, you go to the sample data, and you go to medical studies. They have lipid data as one of the built-in data sets here. Okay, and so let's say, so I'm not really sure what the big takeaway is in this data set, but we can try to predict some stuff and see how well it does, but that doesn't really matter in terms of just being able to interpret the results and things like that. Okay, so in general, when we fit these models to make predictions, we do it in the fit model portion up here. And if we drop in whatever we're interested in predicting, so let's say we're trying to predict in the health industry. So we're going to predict this thing, so some type of blood pressure here. And let's say we want to use, let's use a person's coffee intake and their age, and let's throw in a couple of categorical variables. So these red things say that they're categorical variables. We'll throw in 2 of those. Okay, so I'm going to predict this blood pressure based on these different things. 2 of them are quantitative and 2 are categories. And if we run this model, and I didn't turn on the more reduced version of this, but you can see we get an R squared of 19%. That means 19% of the variability in this diastolic blood pressure can be explained by the model that we built using the coffee intake and their age and their alcohol use and their smoking history. Okay, so using this model, that's how much of the variability in the response we can explain. You can see we have this analysis of variance table here. So you'll notice we don't use the lack of fit table. So we care about the ANOVA table now. We can use this. We can use the parameter estimates table. And we're not going to use the effect tests. Here's our residual plot. It's pretty gross looking. But okay, so what do we got going on over here? A couple of other things in the case that we're interested. Let's stick over here. So notice in the analysis of variance table and the parameter estimates table, we have this coffee intake slope. And so basically what it looks like is that for each additional cup of coffee, your predicted blood pressure is going to decrease by whatever 0.15 is, points in blood pressure. So for each additional cup of coffee, the blood pressure will decrease a predicted amount of 0.15, holding everything else in the model constant. So that's sort of that statement that we add in multiple linear regression, is holding everything else constant. So holding age and smoking history and alcohol use constant. Okay. So you'll notice there's cigarettes, no, and pipes for smoking history. And there's alcohol use at a whole bunch of different levels here. What JUMP does with those categorical variables is it puts them in alphabetical order, and it makes the last one alphabetically -1s, and then it sort of moves that one through. So here, this is when cigarettes is 1, this is when no is 1, this is when pipes is 1, and then there's another category that has a bunch of -1s, and that's similar with this. So if we actually go and look at our data set, and we go to those categorical variables, you'll notice there's a less than 2, is that taken? Yep, so less than 2 is one of the categories. So less than 2 is one of the categories. Greater than 6 is one of the categories. Let's see that here. But you see there's a 0 category, and that's the one that they're leaving blank. So that one's a bunch of -1s. And then with the smoking history, there's a quit. Yeah, quit is the last one alphabetically, so that's a bunch of -1s as well. So if I wanted to predict for those, then I would plug in -1s next to each of these numbers. I didn't bring that over yet. So let's see here. So here's the F-test. It tells us that our model is overall useful, even if nothing in it is. So if I were to ask, do you think that, or do we have statistical evidence of coffee intake influencing the blood pressure? You could do a t-test, and this would say no. It does look like a portion of the smoking history, so this no in smoking history is very, very close. And but otherwise, everything else in our model looks like it doesn't do a whole lot. Altogether, they are more useful. This F-test basically says it's more useful than nothing to use these predictors. And you can see that we have 95 observations. So that helps us in our ANOVA table. So remember, if we have 95 observations total, the corrected total is the number of observations minus 1. For our model, we have n minus the number of betas. And here you can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9 betas. So that gives us, so for this error term, so that's 95 minus the 9 betas gives us 86. And then this difference here gives us the model degrees of freedom, which is also equal to the number of betas minus 1. These two numbers will always add to the total. Similar with the sum of the squares, these two will always add to the total. And then if you divide, so if you were to divide this 1700 by 8, that would give you this. If you divide the 7400 by 86, that would give you this. And then if you divide this 214 by the 86, that would give you this F ratio, and then this p-value is associated with the F ratio. So because the p-value is less than 0.05, that suggests that our model is overall useful. Remember, in that test, it's testing essentially each of the slopes attached to this. So beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, beta 7, beta 8 equal to 0. And then the alternative is that at least one of those is different than 0. So we would say, look, something is useful in our model, although basically just altogether, it seems to be useful. Any one hypothesis test. So if you were to ask if coffee is related, or if age is related, or smoking history is related, or alcohol use individually, if any of those are related, all of those hypothesis tests, you come back and say, no, that's not useful in the model. Again, that's not useful in the model. So any t-test would give you, any individual item, you would run a just a t-test, and those would not come back as useful. Okay, so let's do an interpretation for some of these. So this, with the categorical variables in jump, that's comparing to an average. So this negative 4.58 says that if you've smoked, your smoking history is cigarettes, then we would expect that your blood pressure is 4.58 points below the average across any of the smoking categories. And similar with alcohol use, you could interpret this 1.8, and that would say if your alcohol use is 2 to 6 drinks in whatever period of time this is, but if it's 2 to 6 drinks, then you would expect that your blood pressure will be 1.8 higher than the average across all categories of alcohol use. So that's how you interpret these categorical coefficients. And then at the end of that, you should add holding everything else constant. So that previous statement, that 1.8 is the increase for 2 to 6 drinks, holding everything else constant. Okay. So hopefully that helps with categorical and quantitative, working through the ANOVA table. Remember, if you right-click in this table here and you go to columns, you can get the VIFs, and you can see that we do have a little issue. It seems like the alcohol use here is related to some of the other categories, although the rest of these are below 5. So issues with multicollinearity, potentially with the alcohol use, it seems to be related to something else in the model, but nothing else seems to be causing any multicollinearity issues.